Hello and welcome to Notes 5.4, where we're going to talk about a new type of test, the chi-square test. There are three different chi-square tests that we're going to cover in this course, and the first one is one that is called the test for goodness of fit, which sounds grammatically incorrect, but apparently it is. So, what is this for? So this is, what we're talking about here is looking at categorical data. So the inference we've conducted thus far has been aimed at estimating one parameter, either a proportion or a mean, or the difference between two parameters that we've done recently here. So what if we wanted to analyze multiple parameters at once for a categorical variable? So that's the question here. We've kind of already done this before because we've looked at categorical variable that can be slotted into binary options. Usually like you send out a poll and it's a yes or a no to a question. But like, what if there's multiple answers? Yes, no, maybe, agree, strongly agree, somewhat agree, different sort of options for this categorical variable. What we need is a new model called the chi-square model. This is a family of distributions whose skew is to the right, and if you've seen the in-class demonstration, you've seen multiple examples of this distribution, and that skew is becoming, it's less skewed with increasing degrees of freedom. This time, degrees of freedom is not associated with the sample size, though, okay? So we're going to learn about all three different ways to apply this test. But this first one, the goodness of fit test, which tests whether or not the distribution of counts for one categorical variable from one population matches the distribution predicted or expected, okay? So we're going to try this out. It's often been said that the bathroom stall nearest the door is used the least, and as a result is most likely to be clean. On the television show Mythbusters, that's a good show if you haven't seen it already, the cast tested that theory in a public restroom. The cast observed 119 random people enter a public restroom with 4 stalls and recorded the stall that they used, which isn't creepy at all. Stall number 1, less creepy than watching people kiss. Stall number 1 was closest to the door, and stall number 4 was the furthest from the door. The percentage of subjects who used each stall were, as you can see there, respectively, from door further on. Is this statistically significant evidence at an alpha level of 0.10 that bathroom stalls are not simply chosen at random by people? So let's go ahead and state our hypotheses, but I'm going to let you take a moment to think about what would be the hypotheses here. Notes, if you're going to write it down, we're going to do this in words and not in symbols. So take a moment, pause, and then I'll show you what I came up with. So here are the hypotheses I came up with. Hopefully you said something similar, okay? If not, write this down. You can pause. So the null is that each of the stalls is used just as frequently as each other. So in other words, if there's 4 stalls, that they're used 20% or 25% of the time uniformly, essentially. The alternative, though, is that that's not true. So just that the stalls are not being used with equal frequency. Note that that's not saying any particular distribution, just that like it isn't uniform. It's far enough away from uniform for us to think that it is in fact a uniform distribution of 25% usage across the board. All right, so let's move on to the plan stage. This is where we're going to state what we're doing here, and then we're going to go ahead and come up with some of our conditions here, some new ones here. But first, let's plan. The plan. What we're going to do here is something called, as we have stated before, chi-square test for goodness of fit. Fun fact, known abbreviation for that is GOF. So you can, on the test, write chi-square test for GOF. You don't have to write out goodness of fit. All right, our first 2 conditions are familiar ones, okay, which is randomness, randomization, and independence. So I'm going to go ahead and have you pause and think about those first two conditions. How do we know they're checked off, or what can we assume about this problem? So here we have a random sample was given. Independence was a little bit sneakier here. Something that isn't in the problem that I could make a lot more explicit here is that they actually threw out any case in which a person entered the bathroom and there was already somebody occupying a stall. That definitely would affect independence. So these 119 were entering an empty bathroom where they had all 4 stalls to choose from. So thus, we can assume independence of the stall choice is met here, okay? So if you weren't sure about that one, pause it and go ahead and write it down and process why it's important that we know that the bathroom was actually empty when the people entered. The next thing we need to check off is the counted data condition. For chi-squared tests, we always use counts, raw counts, and not percentages here. Now, the values given above are in percentages. So this is a very important example of where we need to actually come up with what are the raw counts. That will be important when we go to do our work down below in our do steps. But in this particular case, we don't have to do all of it up here. We can just show one example of us converting to raw counts. So we're going to go ahead and use the first example there, which is they tell us that 19.33% of people used the first stall. So what we're going to do is we are going to calculate this out. We're going to go ahead and say stall 1. There's 119, and of them, we have 19.33 or 0.1933. And that, we're going to round to the nearest integer, because when we go to plug this in for our raw count, our calculator might not understand when we're like, yeah, like 12.1 people use the first. That doesn't make any sense to it. It wants raw numbers. So we're going to go ahead and call this just 23, okay? And it's enough to show one example like we have right here. Sometimes the raw counts are given, in which case for this condition, you can just write given. You don't have to show any work for this. So this is explicitly here because sometimes they give it as a percentage and we want the raw count here. For this next condition, expected cell frequency condition, just like in our previous sort of tests where we sort of need samples that are large enough, or, there are some exceptions to that, it's similar here. We need the expected raw count for each particular cell or each particular category or subcategory within our categories to be 5 or larger for this test to work. If we were doing this through just, simulations of like cards and stuff like that, we wouldn't need this, but since we're using a model, it's really important that we have a large enough sort of sample size. So for this condition, what we need is each expected count to be greater than or equal to 5, okay? So in this particular case, and so to check this off, just like above, you actually only need to do one example. You do not need to do all of them. And the smartest thing to do here is to use the smallest one. In this case, that doesn't really hold because they're all equal. We're all expecting each stall to be 25% of the total distribution here. So it doesn't matter which stall you choose in this particular case. If you're dealing with an example where the distributions are not uniform, say eye colors, in that case, grab the smallest percentage and just check that, in fact, you expect to get 5 or more in total. So in this particular case, for all stalls, we expect 119, wrote that wrong, and then times 0.25, 25% of that, okay? Which is 29.75. For expected, it's okay to have decimals. Think back to our like binomial geometric distribution stuff when we talked about expected value. Having a decimal makes sense because you're thinking about in the long run. It doesn't really make sense for a single sample to have decimally accounts in this particular case, but in the long run, we could expect about 29.75 people per stall, which is definitely bigger or equal to 5, so we check that off. So now let's go ahead and move on down to the do step where we're going to go ahead and start our calculation. Now, just as we were doing earlier this unit here, we're going to rely heavily on the calculator. However, there are oftentimes questions about which of the chi-squared components sort of contribute the most to a particular value. And so it's nice to know how to calculate these things. So I always like to sort of maybe start out the calculation and then I sort of dot it and then sort of let it move on forward and let the calculator do the work for me. So I'm going to go ahead in here and write that our chi-square components is always going to be observed minus expected quantity squared over the expected and then the summation of such. If you ever forget that, remember that on your AP formula sheet at the very bottom has our chi-squared statistic right here. So if you ever forget, like, what is the formula? It's right here for you. Observed minus expected, quantity squared over the expected, sum it up, and then make sure that you are always plugging in raw counts, not the percentages here, okay? That's going to be really important. So let's go ahead and go back over here, and I'm just going to actually put in the very first observation here, stall number 1. I'm just going to do the calculations for stall number 1. For stall number 1, we observed that we have 23. That comes from a counted condition there. You can see 23. If I was going to do stall 2, 3, 4, I could do the same thing and using those percentages up in the original problem. Minus 29.75 quantity squared all over the expected of 29.75. And I can continue along with that. I'm not going to, but I like showing that first, like a little example there, okay? Because it reminds me of the formula. It reminds me of how to actually calculate this all. And I can go through and calculate each thing by hand if I wanted to, but the calculator can do it for me. I've already done all the calculations. I'll show you how to do it on the calculator in just a moment. And then I get a chi-squared value of 5.5377. Excellent. The other thing we need to sort of report here is what is our degrees of freedom? Degrees of freedom previously, when we were dealing with proportions, was just your sample, or sorry, with your T model, with your T model of one sample was just the sample size minus 1. When it was difference of means, okay, that was a much different formula, which I did not even show you. Maybe you Googled it and looked at it, which was a little bit wonky. Here it is, how many subcategories are we dealing with minus 1? I'm going to go ahead and write that down. DF, degrees of freedom, number of subcategories minus 1. So in this example, we were dealing with, within our category of stalls in the bathroom, there were 4 of them, 4 subcategories. They had 4 choices from them. So in this case, it's going to be 4 minus 1, which is 3. We have a degrees of freedom of 3. Great. So at this point, it's important to now move over to the calculator. I'm going to show you 2 different ways to do this. The first is when you know your chi-squared in degrees of freedom, but then I'll also show you how to just use the calculator to do the whole do step and find chi-squared as well as your p-value. Let's take a look at how to do a chi-square test on a calculator or find a p-value for a chi-square test. I'm going to show you the first one. So sometimes multiple choice questions give you that this is your degrees of freedom, your chi-squared value, what's your p-value? So let's see how to do that, which is the same way we've been doing it in other tests as well. If you just want to know your p-value with some stats, you can just go to second distribution or the vars button, and you can see that number 7 PDF we never want. We want CDF. We want the cumulative distribution. We want that full probability, and it asks for first lower tail. Lower tail is always going to be your chi-squared value, which in this case was 5.5377. The upper, we want to go into infinity. It's always a right tail distribution, so we're just going to go out as far as possible. We're going to go no, until you're just tired of pressing nines. Degrees of freedom. So in this case, as we just discussed, the degrees of freedom, the number of sort of subcategories, options within your category. Well, there was 4 stalls. We're going to go -1, so it's going to be a degrees of freedom of 3. We're going to hit paste. Enter, and there is our value, 0.1364, and so on. If you're dealing with a calculator that didn't have that fancy menu I just mentioned, notice the order of things here. We got your lower bound, comma, upper bound, and then if I scrolled over, you'd see comma, degrees of freedom. You can use that exact syntax in order to calculate this. All right, so that is the idea behind just finding a p-value from all of this. What if you're doing a free response question and you didn't find all the different values and calculate it all out by hand? Well, in that case, we're going to go to stat. We're going to go over to tests, and we're going to scroll down for a little while. Chi-square test? Question mark? No. Chi-squared GOF, or goodness of fit. That's the one we want right there. Option D. Okay, so be careful of that. As I said at the beginning of the video, there are 3 different chi-squared tests. Turns out 2 of them are option C, but this one is the one we want. So press enter. You'll notice that instead of entering some data, it asks where are your observed and expected values, and they want them in lists, okay? So we are going to go ahead and go over to our lists and put those in instead. So we're going to go ahead and go stat, edit. We're going to go to list 1. We're going to put in the observed values, okay? So remember, the observed values were actually given as a percentage, and we're going to round to decimals. So what you can do is you can go in and type in the sample size, which was 119, and multiply it by your percentage you have there. But what you'll notice is that it gives you a decimal amount, and your calculator will hate that. So do not leave it that way. What you can do is just go back up and press it. Well, that's close enough to 23. Let's do it that way. And you can do it with the next one, 119 times, and it was a 31.93%. Again, that's close enough to 38. I'm just going to go up and press 38. Do not leave it as a decimal. It will not work. I'll continue along here. Notice that I'm just letting the calculator do the work for me. You can do this beforehand to come up with the values. That's close to 34, so I'll change that. Or you can do it like I'm doing right now. Just 119 times, the last one is 20.17, which is basically 24. So those are the observed values there, okay? List 2 is supposed to be the expected values. And as I said, expected can be decimals. It's totally okay. I already calculated it. If you, for some reason, skip that part, we're just coming up with, like, what would it be if we equally distributed these 4 stalls? It would be 25% choice across the board. There's 119 of them, and so if I multiplied that by 0.25, I get this, 29.75. That would be the case for all of these, 29.75. I also mentioned earlier that sometimes they give you problems where the distribution is not uniform. So like if we were talking about eye color, not everybody has eye colors uniformly distributed. Brown is far more common. So in that case, you'd want to use whatever sort of distributions are presented to you. It would never be on you to make it up. So you wouldn't be like, I don't know, like what is it, like 80% brown eyes? They would tell you in the problem what is sort of the population distribution. Now that we have these in our list 1 and list 2, let's go back over to stat. We're going to go to our tests, and we're going to scroll all the way down to the chi-squared GOF. Press enter. So now that we have our stuff in list 1 and list 2, we're good there. Degrees of freedom. Nope. We already talked about this. That's going to be 3. It's already set up for us 3. If not, obviously you change it for the problem. And let's go ahead and go down to calculate. And there you have it, 5.5378, okay? So a skosh off from what we had in our original problem that I wrote down earlier because I was doing it by hand instead. And we have a 0.136394 as it. What's really cool is it gives you the contributions there. The contributions are very interesting for us right there. So why don't we go ahead and see what we can do with that. So the contributions are going to be really important because, like I said earlier, sometimes they ask you which of the particular chi-squared components contribute the most or least or whatever. And so this tells you that first number we're seeing right there, that's the sort of chi-squared component for just the first stall. If we click over to the right, I'm using my right arrow, this tells you for the second stall, and then the third stall, and then the fourth stall. So sometimes they ask in an FRQ about like which of the particular subcategories there is contributing the most to your chi-square. In this case, we would say that second stall. That second stall is, in interpretation, much higher than we would expect, okay? We're seeing that it is 2.2878 as a chi-squared value. So that is, we would expect 0 if in fact it was sort of being as expected. In this case, it is much higher, especially compared to the rest of them. First one's kind of high, second one is much higher. So that's actually interesting because the original sort of hypothesis about this was like, do people use the one furthest from the door? Do people not use the closest one? And it kind of turns out that like, actually, I think people are kind of using that first one. Second one mostly. Like, so it kind of interesting. And not the third one so much. Anyways, so there you go. That's how you can use your calculator to help you through these types of problems without needing to number crunch it all. So in the end, we end up with a p-value. Remember, that does not stand for proportion. It stands for probability of 0.1364. So now we're going to move on to our conclusion. Our conclusion doesn't really change compared to how we were concluding other hypothesis tests. We're going to state sort of our decision about the null hypothesis by comparing our p to our alpha and talk about what sort of evidence we have. We're going to include the context. So in this example here, we're going to say, since p equals 0.1364, which is greater than alpha equals 0.10, we fail to reject the null hypothesis. There is not statistically significant evidence that bathroom stalls are not chosen at random or uniformly. 5 people. And there you have it. So we are not finding in favor of the alternative. We think it basically is a 25, 25, 25, 25 split, and our sample is just a bit different from that, and that's just by random chance alone, not due to anything else going on here. Why don't we go ahead and flip over to the backside? If you need to review any part of this before moving to the backside, do so, because on the backside, we got ourselves a whole new problem here. In his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest level of the game, specifically because March 1st is the cutoff date for youth leagues in Canada, where a lot of NHL players come from. Players born in January will be competing against players up to 12 months younger. This is actually a big deal in like a lot of youth sports, actually. The cutoff dates, people game it. It's really interesting. Look into it. Anyways, the older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and often have a better chance of being successful. To see if birth date is related to success, judged by whether a player makes it to the NHL, a random sample of 80 NHL players from a recent season was selected, and their birthdays were recorded. The one-way table below summarizes the data on birthdays for these 80 players. You can see the distribution there for the 80 different players. The question is, do these data provide convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year? What you'll notice is that an alpha level is not given, okay? So keep that in mind as you go to your conclusion as to whether there's some ambiguity to your conclusion or if you can still like kind of definitively say anything. But check it out. Try this out all the way through, okay? We're going to look for every single part, okay? I want to see your plans, your states, your do's, your concludes. Write it all out. When you come into class, we're going to go over this problem, talk about what questions you have, so be ready. We will see you in class.